Every single day we place our trust in hundreds of engineered objects without even thinking about it. That bridge you drive over, the plane you might fly in, even the chair you're sitting in right now. You just trust they won't fail. But if you ever stop to wonder, how can we be so absolutely sure? How do we build certainty in a world that is anything but certain?
Well, that's what we're going to dive into. We're going to pull back the curtain on the amazing systems that keep our world safe. We'll kick things off with the huge challenge of uncertainty, then look at how we predict the future with probability, how we can test things without breaking them, how we turn mountains of data into clear decisions, and finally, we'll meet these invisible guardians of quality.
All right, so let's get into it. The heart of the problem is this. The real world is, well, it's messy. Materials are never perfectly uniform, temperatures are always fluctuating, and the loads on a structure can vary wildly. A simple model that just uses a single base case or most likely value for every single input, it just doesn't come close to capturing that complexity.
And that really brings us to the central question for any engineer, for any scientist really. How do you design for total reliability when you can't possibly predict every single variable? How do you account for the countless little things that could go wrong?
This right here illustrates the problem perfectly. On the left, we've got this neat, simple model. One input leads to one output. Tidy. But reality is much more like the model on the right. We have to consider a whole range of possibilities. The best case, the worst case, and everything in between. But here's the kicker. Even that isn't enough. You can't possibly test for every single scenario. So what on earth do you do?
Well, you turn to prediction. Instead of building and then breaking thousands of prototypes, which would be incredibly expensive and time-consuming, you simulate them. And this is where we introduce an incredibly powerful tool that lets us explore thousands, even millions, of these what-if scenarios before a single piece of metal is ever even cut.
It's called a Monte Carlo simulation. And honestly, the best way to think of it is like a crystal ball that's powered by pure math. Instead of just giving you one single guess, it runs a simulation over and over and over again. And each time, it uses slightly different random inputs that are based on real-world probability. What you get is a full spectrum of possible outcomes. It's amazing.
So here's the breakdown of how it works. First, you build a basic mathematical model of your system. Simple enough. Then, for every single input that has some variability, think material strength or temperature, you define its probability based on tons of historical data. Step 3 is where the magic really happens. The computer generates thousands of sets of random inputs, all based on those probabilities. And finally, you run the model for each and every one of those sets and analyze all the outputs. This gives you the full range of what could possibly happen and, crucially, how likely each of those outcomes really is.
And this slide right here shows you the very engine of the simulation. On the left, you've got a simple random number, something that's super easy for a computer to generate. The simulation then uses this clever mathematical function to transform that simple randomness into a realistic data point that actually fits the real-world probability of your variable, which you see on the right. This is literally how you turn digital coin flips into incredibly meaningful predictions.
Okay, simulation is fantastic for the design phase, no question. But what about once something is actually built? A tiny invisible crack in a weld or a turbine blade could be absolutely catastrophic. So how do you find these hidden flaws without taking the entire thing apart or, even worse, destroying it in the process of looking? The answer is something called nondestructive testing, or NDT. And it's not one thing. It's a whole family of techniques that act like a kind of industrial X-ray vision. They allow inspectors to see deep inside materials and structures to find defects that would be completely invisible to the naked eye.
And the toolbox for this is just vast. From using sound waves and ultrasonic testing to magnetic fields and magnetic particle inspection, each method is a highly specialized tool. It's kind of like how a doctor uses X-rays, MRIs, and CT scans to diagnose different issues. Engineers use this whole array of NDT methods to find all the different types of flaws that might be hiding.
Let's walk through a classic example just to see how this works in the real world. Imagine you're inspecting a critical metal part for a microscopic crack. First, you cover it with this brightly colored liquid. Then you wipe the surface completely clean. It looks perfect. But then you apply a fine white powder. This powder, called a developer, acts like a blotter, literally pulling the hidden liquid out from that tiny crack and making the invisible flaw brilliantly visible. It's so simple, so elegant, and incredibly effective.
So simulation helps us design things, and NDT helps us inspect them. But both of these processes create mountains of data. Just piles of it. But what do you do with it all? How do you know if a tiny change you made in your manufacturing process actually made your product stronger, or if the test results you're seeing are just a random fluke? You need a tool to separate the real signal from all that random noise.
And that's where this powerful statistical tool called ANOVA comes into play. It's designed to answer one absolutely critical question. If we change something, say the type of fertilizer we're using on a crop, is the difference we see in the result real, or is it just random luck?
Now, this table shows the results from that fertilizer experiment. I know, it might look a little intimidating, but the key to the whole story is hiding in that very last column, the one labeled PRF. This little number is something called the p-value, and it's the number that gives us our answer.
And would you look at that p-value? It's tiny, way smaller than the scientific standard of 0.05. And in statistics, a small number here is a huge deal. It's not just a number, it's a verdict. It tells us with a high degree of confidence that the different fertilizers had a real effect on the crop growth. It wasn't a fluke. But, knowing there's an effect is only half the story. The very next question has to be, how big is the effect, right? Is it just a minor tweak or is it a complete game changer? For that, we look at another number called the effect size.
So in our fertilizer experiment, the effect size is well above 0.14. Which, in the world of statistics, is considered a large effect. So now we know the fertilizer choice doesn't just matter, it matters a lot. It has a huge practical impact. And this is how engineers know exactly where to focus their energy, on the changes that are going to make the biggest difference.
Ultimately, all this analysis, the simulations, the tests, the statistics, it all boils down to this. It allows us to make powerful, data-driven statements of confidence. It's how we move from a world of uncertainty to setting clear, robust, and completely defensible quality standards that ensure a product is safe and reliable.
So when you bring all of these incredible tools together, you get something really remarkable, a complete system. You get a set of invisible guardians working in the background day in and day out to manage uncertainty and to engineer quality into the products we rely on every single day. It's really a four-step dance with uncertainty. We simulate to predict what might happen. We test to see what is actually happening. We analyze the results to understand why it's happening and what's really important. And finally, we standardize to make sure it keeps happening the right way every single time. This is the hidden architecture of safety and quality.
From predicting the performance of a brand new alloy to finding a microscopic crack in a massive pipeline, these methods are the absolute bedrock of modern engineering. But as our creations, from AI systems to quantum computers, become exponentially more complex, it leaves us with a pretty critical question. How will these invisible guardians need to evolve to protect us in a future that we can only just begin to simulate?